Continuous random variables. In this section, we will discuss basic properties of continuous probability distributions and the uniform probability distribution. If we wanted to make probability statements about time or weight, we would need to define these measures as continuous random variables. A continuous random variable is one that can assume an infinite number of values in any interval. If students were allotted 20 minutes to take a quiz, we could define a continuous random variable as the time that it takes the student to complete the quiz. A student could probably complete the quiz between 5 and 20 minutes. This is a continuous random variable because the time for a student to complete the quiz can assume any value between 5 and 20 minutes. For a continuous random variable, we cannot list all of the possible values that the random variable can take on because there is an infinite number of values in any interval, regardless of how small. Because there is an infinite number of values in any interval, the probability of each individual value occurring is virtually zero. This probability would be substantially smaller than trying to find that needle in a haystack. The probability function f of x is the probability density function of the continuous random variable x. Since there are an infinite number of values in any interval, it's impossible for us to talk about the probability of a random variable assuming any particular value. So instead, we talk about the probability of a random variable assuming any value within a given interval. In order for us to determine the probability that a continuous random variable assumes a value in an interval, you must first start by drawing your function f of x. Unlike the discrete random variable, we can't simply plug in the values of a random variable into the function and get probability information directly. Instead, we start by drawing our function of f of x, and then we use this drawing in order to obtain probability information. Here we have the properties of a continuous random variable. First, the probability density function f of x is non-negative for all values of x. And second, the total area under the graph of f of x equals 1. The probability of a continuous random variable assuming a value within some given interval between x1 and x2 is defined to be the area under the graph of the probability density function between x1 and x2. The probability of a continuous random variable assuming a specific value is 0. Because there is no area under the graph at an exact point. In order to find the probability that a continuous random variable x falls in an interval between x1 and x2, we must do the following. First, we start by graphing the probability density function. Second, we must identify the interval of interest on the x-axis. Third, we shade in the area under f of x in this interval. And fourth, we compute the area of the shaded region. The area of this shaded region is the probability that x will fall between x1 and x2. We should note that the probability that x falls in the interval x1 to x2 is the same as the proportion of x values from the population that falls between x1 and x2. The uniform random variable is a popular continuous random variable. The uniform distribution is appropriate whenever it is equally likely that a random variable can take on any value between a and b. For example, if a flight is equally likely to leave any time during the next 10 to 30 minutes, we would say that our leave flight time is uniformly distributed between 10 and 30 minutes. For a uniform probability distribution, the density function is given on this slide. F of x, our density function, is equal to 1 over b minus a as long as x is between a and b, is equal to 0 elsewhere. For this density function, a is the smallest possible value that our variable can assume, and b is the largest possible value that our variable can assume. For the uniform probability distribution, the expected value of x, or the mean value for this random variable, is equal to a plus b divided by 2. The variance for this uniform random variable is always equal to b minus a quantity squared divided by 12. In example 2, the service time at Cal's restaurant is uniformly distributed between 5 and 15 minutes. Let's compute the probability that the time that it will take to service a customer is between 12 and 15 minutes. The service time is uniformly distributed between 5 and 15. Therefore, the smallest possible service time is 5, and the largest possible service time is 15. Our a value is therefore 5, and our b value is 15. Our probability density function for this uniform random variable is f of x, which is 1 over b minus a, and for this example, that's 1 over 15 minus 5, which equals 1 over 10. So our density function value is 1 over 10 for all values of x that are between 5 and 15, and this density function is equal to 0 everywhere else. In order to compute the probability that a uniform random variable falls between 12 and 15, we should follow our steps for computing probabilities for continuous random variables. Recall, first we graph the density function. Second, we identify our interval of interest. In this case, it's the interval between 12 and 15 on the x-axis. Third, we shade in the area under f of x in this interval. And fourth, we compute the area of the shaded region. So in step 1, we draw our density function. The probability density function for a uniform random variable will always be a straight line segment. The height of this line segment will always be at 1 over b minus a. For our example, our height is 1/10, and this line segment will always fall between a, the smallest value your random variable can take on, and b, the largest value that your random variable can take on. Since our probability question is asking about the interval between 12 and 15, we should identify this interval on the x-axis. In step 3, we shade the area under our function in this interval. And in step 4, we compute the area of the shaded region. For a uniform probability distribution, our shaded regions will always be a rectangle. The area of a rectangle is always the height times the width. So for our example, the height is 0.1 or 1/10, and the width is 3. Therefore, the area of our shaded region is 3 times 1/10, which is equal to 3/10. Following our steps, we have determined that the probability that it takes between 12 and 15 minutes for a customer to get service is 0.3. Therefore, we can conclude that there is a 30% chance that customers will wait between 12 and 15 minutes for service at Cal's restaurant. For our example, the expected or average service time is A plus B, which is 5 plus 15 divided by 2. For our example, there is an average 10-minute waiting time for service. The variance for service time for our example is B minus A quantity squared divided by 12, or 15 minus 5 quantity squared divided by 12. So the variance is 8.33 minutes. Example 3. Suppose the flight time between Cleveland, Ohio and Atlanta, Georgia is uniformly distributed between 70 and 90 minutes. What is the probability that this flight time will take more than 80 minutes? What is the mean flight time, and what is the variance of the flight time? For this example, our density function is f of x equals 1 over b minus a. Recall for this example, our smallest possible flight time is 70, which means a equals 70, and our largest possible flight time is 90, which means our b is 90. Accordingly, our density function is 1 over 20, which equals 0.5. This is our density function for x values between 70 and 90. Our density function is equal to 0 elsewhere. For our example, our density function is drawn as a line segment between our a value and our b value. So it's drawn as a line segment between 70 and 90 with a height of 1 over b minus a, or for our example, our height is 0.05. In step 2, we identify the interval that we're interested in. For our example, we were asked the probability that it takes more than 80 minutes. Therefore, we highlight the interval 80 or greater. In our next step, we shade in the area under our density function in this interval. And in our last step, we compute this shaded area. This shaded area is the probability that the flight time will take more than 80 minutes. This shaded area for us has a height of 0.05 and a width of 10. Therefore, its area is 10 times 0.05, which equals 50. We can state that the probability that x exceeds 80 is 0.5. Our mean flight time is a plus b divided by 2, or for our example, our mean flight time is 80 minutes, and the variance of our flight time is equal to b minus a quantity squared over 12, or 33.33 minutes. Now let's get some hands-on practice. The time that it takes students to complete a quiz is uniformly distributed between 20 and 30 minutes. What is the probability that it takes a randomly selected student less than 28 minutes to complete the quiz? You should pause the video at this time and try to complete this problem. You should have started by identifying your A value as 20 and your B value as 30. You then should have determined your density function, which is 1 over B minus A. For this example, it's equal to 1/10, as long as x is between 20 and 30, and it's equal to 0 elsewhere. Next, you should have drawn your density function as shown on this slide and identified our interval of interest, which is less than 28. Next, you should have shaded in the area under our density function in this interval and computed that area as having a height of 0.1 and a width of 8. Therefore, the probability that x is less than 28 is equal to 8 times 0.1, or 0.8. The mean or expected time to complete the quiz is equal to a plus b divided by 2. For this case, it's 25 minutes. And the variance to complete the quiz is equal to b minus a quantity squared divided by 12, which is 8.33 minutes.